This is a problem on rotational dynamics from chapter 7, number 68. I'm redoing this one because I messed up when I did it in class. And so I'll walk you through this. The problem involves a pulley on a frictionless axle, and there is a force being applied down on the right-hand side of 10 newtons to a string that is attached to the pulley. And on the other side, there's a 1.5 kilogram mass, and the system is accelerating. 1.5 kilograms has a weight of about 15 newtons, so there's more downward force on the left than on the right. So we know that this thing will be accelerating down to the left. The mass of the pulley is 2 kilograms. And it has a diameter of 50 centimeters, which is 0.5 meters. And the question is, how long does it take the block to move 30 centimeters? So that's a question about time and distance, which are kinematic parameters. So we can start off by asking ourselves, what kinematic parameters do we have and which ones do we need to figure out? We are told that it starts from rest, so the initial velocity is 0. The distance we're interested in traveling is 30 centimeters. We are looking for the time. We don't know the final velocity it'll be moving at the end of that time, and we don't know the acceleration. This object is not in free fall because there is a rope attached to it. So it's not just gravity acting on it, so we don't know the acceleration and we don't know the final velocity. So in order to answer this kinematics problem, we're going to need to figure out either VF or A in order to get T. A is what we're going to go after because we know something about the forces that are acting on this. So we'll use Newton's second law to figure out the acceleration of the object. So let's draw a free body diagram for that object. Here's that 1.5 kilogram object. There's a rope attached to it with a tension T, and then there's the weight acting down, which has a magnitude of 1.5 kilograms times 9.8 meters per second squared, which gives us a downward force of 14.7 newtons. And we know that the sum of those forces acting on that object equals its mass times its acceleration. So what are the forces? For this object, I'm going to have this way down be the positive direction. It's accelerating that way, so that's the only reason I'm choosing that to be positive. So that means W, which is down, is positive, minus the tension in the rope, T, equals 1.5, that's the mass of the object, m, times A. So since we know W, that gives me 14.7 minus T equals 1.5 times A. Well, I don't know what T is. You might be tempted to say, well, that's the tension in the rope, and isn't that 10 newtons? But this rope is not sliding freely over a frictionless pulley. It is attached to this wheel, and this wheel has inertia. So the tension over here on the left is not the same as the tension on the right. So now we have to consider the pulley, or the wheel, and it has two forces acting on it, a tension down on the left and then 10 newtons down on the right. And the sum of the forces, or the sum of the torques rather, acting on that wheel are equal to its moment of inertia times its angular acceleration. And its angular acceleration is related to the tangential acceleration of some point on the surface or edge of the wheel. So if I know the angular acceleration of the wheel, I also know the acceleration of this rope down. And they are related by the angular acceleration is A over R. A is equal to alpha times R. It's our usual conversion from angular to linear values. So let's now take a look at what we get next. The sum of the torques. I have the torque due to the tension in the rope is T times R. That's the torque on the left-hand side going in the counterclockwise direction, minus the 10 newtons times R. That's the torque acting in the clockwise direction to oppose the motion, and that equals I times alpha. For the pulley, which is a flat disk, the moment of inertia is 1/2 mr squared. In this case, m is the mass of the pulley, which is 2 kilograms, and r is the radius of the pulley, which is 1/2 the diameter, so it's 0.25 meters. So that gives me the moment of inertia is 0.5 times 2, which is 1, times 0.25 squared is 0.0625 kilogram meters squared. So I have T minus 10 times R, which is 0.25. I've taken this part, I've factored out the R, so it's R times T minus 10 equals I, which is 0.0625, times alpha, which is A over R. Okay. Now I have two equations that have T and A. This one from the pulley and the one up here for the linear motion of the block, which is 14.7 minus T equals 1.5 times A. So since I want to solve for A, what I'm going to do is combine these two equations to eliminate T. What I'll do is I'll solve this equation for T. It gives me T equals 14.7 minus 1.5 times A. I'll then take this and substitute it into the equation for the pulley. I get 14.7 minus 1.5A, that's T, minus 10 times 0.25 equals 0.0625 times A over R, which is 0.25. And now I have an equation that's just an algebraic equation for A. So I'll reduce it. 14.7 minus 10 is 4.7 minus 1.5A times 0.25 equals 0.0625A over 0.25. So I'll expand this out, and I get 1.175 minus 0.375A equals 0.25 times A, which gives me 1.175 equals 0.625A. Then I get finally A equals 1.175 divided by 0.625, which gives me 1.88 meters per second squared for the acceleration. And then I can finally take that and put it back into my table of kinematic parameters, and I have x, vi, vf, a, and t, 0.3 meters, 0, 1.88 meters per second squared, and I'm looking for the time. I use x equals vit plus 1/2 at squared, and that gives me 0.3 equals 0 plus 1/2 times 1.88 t squared, which gives me t equals the square root of 0.6 divided by 1.88, which is 0.565. seconds.